Hello everyone. Our group composed of myself Bharat, Dylan, Jack and Leonie are going to present our final project on implementing the algorithms discussed in the paper Risk Prediction in the Life Insurance Industry using Supervised Learning Algorithms. We had discussed this paper in the paper presentation assignment. Now we are going to talk about how we perform exploratory data analysis, data pre-processing, data reduction, implementation of classification algorithms, and then discuss the results of what we obtained in our study. We will start with a short review of the classification problem in the life insurance industry. Daniel will cover bivariate and multivariate EDA to get a sense of the data and test initial hypothesis. Leonie will then talk about the little's test to test whether our data was missing completely at random and how she used the mice algorithm package in R to impute MAR data. I will then cover the PCA and CFS. I'll then cover logistic regression. Leonie will discuss neural networks, and then I'll talk about random tree and rep tree. Finally, we will conclude by comparing the results of these algorithms on our test data and suggest areas for further work. The importance of correct risk prediction cannot be overemphasized in the life insurance context. Life insurance companies have to be careful about whom to insure and whom not to in order to stay financially solvent. While there is no perfect formula to determine insurability, actuarial tables have been traditionally used, but they are quite time consuming. Predictive analytics offers a promising alternative to the risk prediction task. In our study, there are 8 risk levels, with 1 being the lowest and 8 being the highest. There are 117 variables like health indicators, product information, medical history, and employment information. The classification task here is to predict the risk level based on these attributes. Dylan will now cover the EDA part. In the interest of time, he is covering only bivariate and preliminary multivariate analysis here, as we have covered univariate analysis in our paper presentation video.
Thanks, Barrett. For a dataset, exploratory data analysis, also known as EDA, is designed to understand its main characteristics via visualization. It provides tools and insights for us to develop an appropriate model. We are only introducing some representative aspects of EDA here. The response variable for this study is ordinal with 8 levels, with highest frequency in level 8 and lowest in level 3. This targeted variable is related to the final decision associated with insurance application. In bivariate analysis, we detect whether each continuous variable has impact on the response risk level using data visualization. This figure suggests each has a significant impact on the risk level. Level 8 looks quite different to the others. This figure shows height varies according to the different response groups. Again, level 8 is the least similar to the others. The figure denotes weight has an influence on the risk level. Different risk levels has different regions, and the shape indicates that there is likely to be some roundings going on. The bar plot reveals the body mass index is different across response groups. By comparison, level 2 and 5 are relatively high, whereas level 4 and 8 are relatively low. Since normalized age, height, weight, and body mass index are key metrics of interest based on previous perception, we investigate a bit further using multinomial logistic regression, assuming low collinearity, as well as independence of irrelevant alternatives. Using two-tailed z-test, we compute significance levels respectively and summarize them in the left table. It indicates that all 4 continuous variables are statistically significant overall, despite a few weird-looking p-values in the red cells. Now Leonie will cover the data preprocessing part.
Hi everyone, my name is Leonie, and next I'm gonna talk about data preprocessing. The reason why we need it is the original dataset is not perfect. It has a lot of missing entries, and many features provided are actually irrelevant to the response variable. Therefore, the general goal of this step is to remove the noise in the dataset and impute the missing data. To do so, first we need to detect the missing value in the dataset and impute them based on their missing mechanism. Second, to reduce the dimensionality of features that would be later used in the models. From the missing value plot, we can see there are actually a lot of missing entries in the dataset. So the first question we might ask is, what's the pattern of the missing data? In general, there are three kinds of missing mechanism: missing completely at random, missing at random, and missing not at random. To determine the missing pattern, first we need to run a statistical test called the little test to test if the missing data is missing completely at random. And the little test indicates the missing data is not missing completely at random, as the null hypothesis is rejected at 5% significance level. So it can only be either MAR or MNAR. And from the missing value plot again, we can see there is no clear pattern of the missing data. Therefore, we assume that the missing data is just missing at random. Under this assumption, we can proceed to the missing data imputation. First, attributes with more than 30% missing were dropped, so 128 attributes are now reduced to 117. Now we can use MICE, which is multivariate imputation by chain equation, a built-in library in R to impute the remaining attributes, and the number of imputation we use is 5 by default.
Now I will talk about the intuition behind the correlation-based feature selection method. CFS selects features from the original feature set based on the principle that the features in the selected subset should correlate well with the output but should not correlate well with each other. The CFS algorithm selects k features from the original feature set and then calculates a merit score based on the formula shown here. The numerator consists of the sum of correlations of features in the feature set with the output variable denoted by C here. So the higher the sum, the higher the merit score will be for that set of features. In the denominator, we see a term that has the sum of the product of the correlations taken two at a time. So the higher the correlations between the features in that set, the lower the merit score would be. The goal of the CFS method is to rank the sets of selected features and then choose the set of features that has the highest rank. So the YCATU environment for knowledge analysis, known as WAKA, is a free data mining software licensed under the GNU General Public License. It can be used for performing data reduction techniques like the PCA and the CFS. The WAKA interface is shown on this slide. To do the CFS, we choose the best first method and the CFS subset eval evaluator. CFS then chooses the number of attributes itself. Now coming to the results of the CFS, the key things to note here are that the merit of the best subset which has been found is 0.514 and the number of subsets evaluated was 3200. The algorithm has selected 33 attributes and these attributes have been listed in the WAKA output window. Some of these attributes are age, BMI, medical history and so on. We got the same attributes as the authors and have used them for our algorithm subsequently. Now we move on to the PCA. We uploaded the raw dataset to WAKA and used the default settings of the PCA feature selection. The measure of variation captured by a PCA variable is indicated by its standard deviation as shown by the small circle on the right in this figure. The higher this value, the greater the variation captured by that variable. The PCA feature ranked 1 by WAKA had a standard deviation of 2.451. As per the paper, we selected all features that captured at least 50% of this maximum standard deviation value, that is up to the 28th feature that has a standard deviation of 1.247 as shown in the next slide. Next, we are going to apply the supervised learning algorithms on the datasets that we have obtained from the CFS and the PCA methods. The authors have used mean absolute error and root mean square errors to evaluate their models, and we have also used these two metrics. This slide provides the formulae. We found that for classification problems, the classification error could perhaps be a better metric than these two measures. We discuss this issue in greater detail in the concluding section. Now I will talk about the implementation of logistic regression model for our dataset. Logistic regression is a natural choice for a multi-class classification problem such as this one. We tuned the hyperparameters of logistic regression using grid search. The hyperparameters that we considered were the C value, which is the inverse of the regularization factor lambda, for which we used 5 values in the logarithmic scale ranging from 100 to 0.01, and the solvers Newton CG, LBF, GS, and Live Linear. Grid search yielded the optimal value of C as 100 and the solver as Newton CG. We got the MAE and RMSE values shown in the table for the test data. The CFS dataset had lower MAE and RMSE scores than the PCA dataset. As we use logistic regression instead of multiple linear regression, we do not have a head-to-head comparison with the paper. We, however, feel that logistic regression is a better choice for this dataset. Leonie will now talk about the implementation of the artificial neural network.
Next, let's talk about the artificial neural network. Since the author of the original paper didn't really state which neural network models it used, we chose a single hidden layer neural network as it is usually sufficient for the large majority of problems. The graph on the right is a simple illustration of a single hidden layer neural network. So for each data point, the attributes are entered into the input layer, and the hidden layer in the middle does a linear and nonlinear transform of the inputs, and then output them into the output layer. We run a tenfold cross-validation on both of the CFS and PCA results. And the table shows the numerical values of MAE and RMSE are pretty close to the author's results. And we can interpret the MAE as the average absolute deviation of the predicted risk level from the true risk level, and the RMSE as the average square deviation of the predicted risk level from the true. Both of the MAE and RMSE of CFS is lower than those of PCA. So in our study, as for artificial neural network, we report that CFS does a better job than PCA, and the average absolute deviation of the predicted risk level from the true is about 1.37.
Now I'm going to talk about how we implemented the random tree and the reduced error pruning tree algorithms on our datasets. Firstly, a brief intuition on how these algorithms work will be helpful. Random tree and rep tree are both decision trees but work in different ways. On the left, we see a decision tree. In a standard tree, each node is split using the best splitting feature among all variables. In a random tree, each node is split using the best feature among the subset of predictors randomly chosen at that node. So in essence, a random tree is a decision tree that selects features at random for splitting data at nodes. On the other hand, rep tree or reduced error pruning tree is an algorithm that does pruning to create a tree. Initially, a complete tree is constructed through a standard decision tree construction method, and after this, the algorithm uses a holdout dataset to compare each parent node and the children node pairs from the bottom-up direction to see if there is any subtree where the error of the child node is higher than the error of the parent node. For example, in the figure on the right, the error of one child node in the red colored boxes is higher than the error of the parent node. In such a situation, RepTree will delete the children nodes and will make the parent node as the leaf node.
Now I'm going to cover how I implement the reduced error pruning tree and the random tree algorithms on both CFS and the PCA datasets and what the results are. First of all, reduced error pruning tree makes use of regression tree logic to create trees in different iterations. ANTI develops its model by information gain and variance deduction. By bias-variance trade-off, reduced error pruning tree tends to produce a simple model with large bias but small variance compared with other decision tree methods. Particularly, I implemented this algorithm in R by using the rpart package, which the function rpart is used to build a single tree model, and the function prune.rpart is used to prune the tree in order to avoid overfitting. With just several lines of code to build the tree and to tune the hyperparameters afterwards, I have two models which produce similar accuracies while predicting the test datasets, compared with the results that the researchers have shown in both PC and the CFS cases. So I got 2.05 of mean absolute error, 2.45 of root mean squared errors in both cases. However, the misclassification error rate of my models are astonishing 81%, which means that my reduced error pruning tree models are not good at all. Since my models can produce similar root mean squared errors and mean absolute errors compared with the results that the researchers reported, then it is thought that the researchers did not provide a good model for this dataset as well. Additionally, random tree is another decision tree algorithm which focuses on estimating class probabilities and selecting a subset of attributes randomly. So I implemented this algorithm in R using the ranger package, which the function ranger creates a random forest by using some of the attributes in the dataset. This time, in both PC and the CFS cases, the mean absolute errors are 1.39 and 1.54, and the root mean squared errors are 2.41 and 2.52 respectively. However, again, my models have a very large misclassification errors, which are 0.48 and 0.54 respectively. Note that my root mean squared errors and the mean absolute errors are very close to what the researchers have shown in the research paper. So this also indicates that the random tree models that the researchers have is not good enough. But the good news is the random tree models are much better than reduced error pruning tree models when comparing the misclassification errors. Therefore, based on the research paper and my observations above, it is obvious that reduced error pruning tree and the random tree algorithms do not have a good predictive performance on this dataset, which is against the result that the researchers propose. It is thought that in classification scenarios, mean absolute error and the root mean squared error is not good enough to describe the predictive power of the models, considering that the misclassification error rate is very large in this dataset. Some other machine learning algorithms can be implemented here. But I do not guarantee that these models can have a better performance.
We conclude our presentation by discussing the key findings that we got by implementing this paper. The table containing our results and that of the paper is shown below. Our MAE and RMSE results closely matched and were even lower than those obtained by the authors of the study for the neural networks and web tree algorithms. As our technical contribution to this paper, our key finding was that for a classification problem like this one, the classification error is a better metric than RMSE and MAE. Risk level is an ordinal type variable, and therefore a classification measure could be a more appropriate measure here. For example, while risk level 8 is certainly higher than risk level 5, which is in turn higher than risk level 2, we cannot say that risk level 8 is 3 steps higher than risk level 5, which is in turn 3 steps higher than risk level 2. Therefore, in order to check how our algorithms are performing, we felt that it would be more appropriate to check if they are able to classify level 8 as level 8 and not as a level 5. We evaluated the algorithms for the classification errors and found them to be quite high as listed in the table below. So as a next step, work can be done to devise either new algorithms or improve these existing algorithms to reduce the classification error rates. Finally, we would like to state that we found CFS to be a potentially valuable supplementary dimensionality reduction technique to PCA. While PCA is much more well known and widely accepted, the relatively less known CFS yielded results with comparable and in some cases even better accuracy, along with the significant benefit of model interpretability, as CFS does not modify existing variables by combining them. With this, we conclude our presentation and hope you could learn something new about how classification algorithms are used in life insurance prediction tasks from our work on this paper. Thank you very much.